Hello friends, welcome to this third part of experiment number 4. So in the previous two videos, we have already covered your SR and D flip-flop. To finish off the last part of this video, which is nothing but the last part of this experiment, which is nothing but your JK flip-flop. Okay. So today we will have a glance on the code of your JK flip-flop, and we'll also check how to verify this flip-flop. So the symbol of your JK flip-flop looks something like this. So it is very similar to your SR flip-flop. As all of you know, JK and SR are very similar. But what is one small difference? The one small difference here is nothing but in SR flip-flop, you are getting a forbidden state. In SR flip-flop, you are getting a forbidden state. In order to avoid that forbidden state, we have come across your JK flip-flop, wherein we will be replacing that forbidden state with a toggling condition. That is one small change between your SR flip-flop and JK flip-flop. So in exam, most of the times your examiners will be trying to see the last combination, which is 1-1, which will provide you the toggling condition. So you can just have a look at the truth table here, friends. So the clock is high in all the instances. So when it is 0-0, no change, or you can say the previous condition is continued. When it is 0-1, the flip-flop is reset. When it is 1-0, it is set. And when it is 1-1, it is toggling. It is toggling between Q and Q bar. Okay. That is, it will produce 1 and 0, 1 and 0. So in exam, the examiners will try to look upon this last condition. Why? Because only this condition is differentiating your SR and JK flip-flop. So if you get this condition, your JK is working properly. It means that your JK is working properly. Okay. So let us now quickly move ahead with the code. So this is your JK flip-flop code. Okay, I hope so it's visible. And yeah, again here, if we start from the beginning, you already know regarding this time scale. Let us not waste time on that. Let us quickly jump to the main logic of your code. So module followed by the name of the module, which is JKFF. So inside bracket, you are written your all the inputs and outputs. So JK, again, we are taken and it has only one variable, only simple reason because again, you already know we will be applying your case statement. So inside case statement, we are taken JK as one variable. So that means input must be 1 down to 0. That is JK naught and JK1. It means that your J will become JK naught, your K will become JK1. That is the difference. Why? You are told the reason, because we will be applying the case statement. Okay. So output has been defined. Then the same output will be defined in the form of a resistor. So we'll start with your sensitivity list. So always at the positive edge of the clock, most of the times. Here we are mentioning JK as well. Just an experiment for you guys. Remove this JK, just put the clock and try whether you will be getting the proper output or not. You can write out with the code. Okay, so always at JK, comma positive edge of the clock. So begin. 0, continue with the previous state. When it is 0-1, when it is 0-1, the flip-flop is reset. When it is 1-0, it is set. And when it is 1-1, it is toggling. That's all. Very simple code, friends. The logic is pretty simple. Very similar to a SR flip-flop. Just change one condition, which is 1-1. And finally, your QB is nothing but it is not of the negation of your output Q. So end this case. Here we are ended with the case. Here end this always, and finally end the module. Okay. So this is all regarding your JK flip-flop. So to this we will be writing a test bench. So test bench remains the same for as I was telling you, for almost all of the flip-flops the test bench will remain the same. So your inputs here are mentioned in the form of a resistor, that is JK, and clock. Outputs are mentioned in the form of your wires, which is Q and QB. Very important step, this one, you need to link your main logic of your JK with this test bench. How do you link? By keeping the same name as your JK flip-flop, the keeping the same name of your main code. So the main code is what now here? JKFF. So even here, what it should be? It should be the same, JKFF. Followed by your instance name. Your instance we have taken JK1. You can put your own name also, no problem. then all your inputs and outputs. So here when we are initializing the clock, the same way how we have done in your all the previous flip-flops, we have initialized clock is equal to 0. Next, we have generated the clock here. How to generate the clock? By negating the clock. So while you negate the clock, very important step, this less than symbol. It should be less than or equal to clock. So start executing here. So here we have written all the combinations of your input starting from 00 to 11. So you can observe here, initially it is 00, after 15 nanoseconds, 01, and so on. Finally, this initial block is for the visibility of your output. So visibility of the output is possible how, friends? With the help of your monitor. Okay. So make sure you use the same order or sequence. So JK is first. So therefore here also I write JK first, because this of the simple reason the mapping should happen properly. Whatever the mapping happens, that should happen. So you know how to implement it. Click on implementation and do the check syntax. Go for simulation. Click on the top module. Don't expand it. Don't expand it and click on the lower module. Click on the top module. Okay. Then do the behavioral check syntax. Finally simulate your behavioral model. So the simulation is done. If I want to see the outputs in the form of the waves, again click on this fit to screen, that is zoom to full view. So you can just observe here when the clock is high. When the clock is high, just click. When the clock is high, both the inputs are 00, so you can see it is a reset. Okay. Next, when the clock is high, your J and K is 10. That means it is set Q is equal to 1 and Q bar is equal to 0. Finally, the last very important condition. When it is 1, 1. When it is 1, 1, you can see here the first condition, Q is 0 and Q bar is 1. We want a toggling condition, right? So here you can observe again at 1, 1, your Q has become 1 and Q bar has become 0. Here it was 0, 1, here it is 1, 0. So therefore it is toggling when it is 1, 1. Okay. The same thing can also be seen in the form of the console, in the form of the variables here in the console. Okay. So this is all regarding your experiment number 4. We have covered all the 4 flip-flops, sorry, all the 3 flip-flops, but in different videos. The only simple reason, because if you want to see a particular flip-flop only, then you can just see that particular video. That was the reason why we did it with 3 parts. Okay. So if you have any doubts with in regard with these flip-flops or in regard with any of the experiment, you can just message yourself. Thank you for watching. We'll again meet up in the next video.